Alright, so hopefully you've had a chance to look at these example problems. If not, go ahead and print the PDF off and try to answer these questions and then come back to the video. Alright, so this first question asks, a nail has a cross-sectional area of 0.11 centimeters squared. If you try to stand on a nail, it would pierce your skin. However, you can lay on a bed of nails without injury. Calculate the pressure of a 60-kilogram person standing on a single nail. All right, so we just want to compare these two cases. First of all, recall that pressure is the force exerted divided by the area. So we need two pieces of information to calculate the pressure. We need the force and the area. The force needs to be in newtons, and the area needs to be in meters squared. We're actually given the cross-sectional area in the problem statement of 0.11 centimeters squared. So if I take the area of 0.11 centimeters squared, I can take this and turn it into meters squared. So notice that there are 2 centimeters, so I need to convert both of them. And I'm going to do that by putting 2 conversion factors right next to each other. And when I do that, I get 0.0000011 meters squared. I should also say that this is the cross-sectional area of the nail, not the tip of the nail. So this would be a nail that's been blunted. All right, we know that the force is mass times gravity. So that's 60 kilograms. This is the person's mass. Gravity is 9.8 meters per second squared. And the area is what we just calculated, 0.00011 meters squared. So this is going to give us the answer in in pascals. So this is 53 million, and I'm going to round here, 53,500,000 pascals. That's a lot of zeros. Sometimes we do use other units like kilopascals, or in this case, megapascals would be appropriate. But this would be equal to 53,500 kilopascals. All right, so if that same person is laying on a bed of 1,000 nails, what this does is it changes the area. So the force is the same, 60 kilograms. But if the person's body weight is distributed over those 1,000 nails, we now have a new area, which is 1,000 times the area of one nail. And so this gives us 0.011 meters squared. So with this new area, we can calculate the pressure of this person laying on the nail bed. And this is 60 kilograms times 9.8 divided by the area. And this gives us 53,500 pascals, or 53.5 kilopascals. Notice that this is 1,000 times less pressure than standing on one nail, as it should be, because we are spreading that force out over 1,000 nails instead of just one nail. All right, question 2. In 2018, Hurricane Michael made landfall on the Gulf Coast, At Tyndall Air Force Base, the maximum wind gust measured was 139 miles per hour. After that, the sensors failed. At this wind speed, the pressure exerted on a wall perpendicular to the wind is 2,400 pascals. What force would this wind exert on a building that is 6 meters tall and 13 meters wide, the size of an average 2-story home? So first, let's just sketch this problem out. We're looking at the side of a building like this. So this is the side of a house. The wind is coming in this direction right here, perpendicular to the house. And so here's the rest of the house. All right, and then we want to know what is the load on this house. What's the force exerted? So we know that pressure is force divided by area. Well, if I simply multiply both sides of the equation by area, I get an equation for force. Force is the pressure times the area. So we can simply plug in what we know, which is the pressure is 2,400 pascals. The area of this building is, if we assume it's rectangular, is 6 meters times 13 meters, which is 78 meters squared. So I'm going to multiply this by 78 meters squared, the pressure, and that's going to give me the force. This is 187,200 newtons. Now that might not sound like much, it might sound like a lot. So let's convert this into pounds just so that you kind of have an idea of how big this force is. So given that 1 pound is 4.4 newtons, how many pounds of force is this? So we can take our force, which is 187,200 newtons, and simply multiply it by 1 pound over 4.4 newtons. And this gives us 42,500 pounds. So this kind of gives you an idea of why buildings fall down in hurricanes. They get blown over from the force of the wind. This is quite a large force. All right, question 3. How does the buoyant force work? We didn't talk about this in class. So I thought I would mention this in the video because I think it's kind of just an interesting application of Newton's laws and what we've learned so far. So let's first just kind of sketch out a little problem. We're going to look at something, just a rectangular box underwater. So here's the surface of the water. And then I'm going to put a rectangular box down here in the bottom. We're just going to look at it from the side. So here's my box. All right, and then let's go ahead and label the pressures that are exerted on this box. I have a pressure from this side right here. I've got a pressure. This is a side pressure, which is equal to the force divided by the area. I've got another pressure over here, which is also a side pressure. I've got forces acting all around it. I've got a force down here. We just call this our bottom pressure. I've got a pressure up here, which is the top pressure. Okay. Now, if you recall from class, what was the one variable that affected pressure in a fluid? Because we're underwater, so we are in a fluid. What is that one variable? And that one variable is simply the depth. So if I just kind of sketch out a line here, I would have a line for the top and a line for the bottom. So this is the depth of the top of our box. So we'll call this the top depth. And then down here we have the bottom depth. Notice that the top depth is not as deep as the bottom depth. That might be obvious, right? But how does that affect the pressures? What does that mean about the top pressure and the bottom pressure? It means that the bottom pressure, we can write this as an inequality, the bottom pressure is greater than the top pressure. And that's because it is deeper. Well, what do we know about pressure? It's the force divided by the area. So the force at the bottom divided by its area is greater than the force at the top divided by its area. Now we could just take an arbitrary area of, say, 1 meter squared, and we notice that in that case, the bottom force is greater than the top force. So if I wanted to draw this out in with magnitudes, I would say that the bottom, this is the force vector now that we're going to write. This is the bottom force. And then we have a top force. Well, if the bottom force is greater than the top force, then we're going to have a net force acting up. Now, if you recall from drawing force diagrams, you also know that gravity is pointing down. So these are not the only two forces acting on our object. There's also gravity acting down. And so without gravity, of course, everything would just float. So we've got gravity pointing down, which may be greater than the buoyant force, in which case it would sink. All right, now what about these side forces? Notice that the side forces are all at the same depth. So they cancel each other out. So we got a side force on the right and on the left, and they're at the same depth, so they don't affect the motion of the object. All right, number 4, a gas is initially at 200 kilopascals in a volume of 3 liters. The volume is changed so that the new pressure is 500 kilopascals. What is the new volume of the gas? All right, so let's go ahead and recall from class. This is Boyle's law, which says that the product of the pressure and volume of a gas is equal to a final pressure and volume, provided that temperature is held constant. So all I need to do is plug in my initial pressure, which is 200 kilopascals, and volume, which is 3 liters. Let's put those on the left side. There's my initial pressure and my initial volume. And then on the right side, I have my final pressure, and I don't know the volume. So I'm just going to put in 500 kilopascals, and then my final volume, which is V2. I want to solve this equation for V2, so I'm going to do that by dividing both sides by 500 kilopascals. On the right side of the equation, my kilopascals cancel, and I'm just left with V2 all by itself. On the left side, the units kilopascals cancel, and then I'm left with 200 times 3 divided by 500, which gives me 1.2 liters. Notice that this is smaller than the starting volume. So V2 is smaller than V1. Does this make sense? Let's think about it. The gas was initially at 200 kilopascals. So over here I've got 200 kilopascals. It was finally at 500 kilopascals. So think about trying to increase the pressure of a gas. Would you do that by making the volume smaller? Yes, we would. We would push the gas into a smaller space, which would increase its pressure. So this makes conceptual sense as well. All right, I want to go over to the simulations that I showed you earlier today just to take a look at gas simulations. So this is at phet.colorado.edu. If you're interested, I would suggest going to this website. So you can just Google or internet search PHET, and it'll be the first hit that you come to. This one's a gas one, and I wanted to show you a couple of things about this. And we can adjust the different variables by, for example, taking this little handle over here and changing the volume of our container. So I can change the volume of the container. I can also change the pressure by adding gas. So we can just pump in a little bit of gas there, and we get more pressure. I can also change the temperature. I can heat it. There it goes, going up and up. I can also cool it down. Okay, and of course, if we heat it up too much, we exceed the container's capacity, and the lid pops off. So there it all is, all coming out now. Okay, so I want to take a look real quick. I'm going to set this to 10 nanometers width. So the width now down here at the bottom is 10 nanometers. It's that scale down there at the bottom. Okay, so notice, let's go ahead and cool it back down somewhere closer to room temperature. Let me put this in degrees Celsius. So room temperature in degrees Celsius is about 20. So there we are. We're at 20 degrees Celsius. We've got right around, if you notice, about 1,000 kilopascals, okay? So this is relatively high pressure, but that's okay. Just want to notice what happens when I hold the temperature constant. I'm going to hold temperature constant. So we can do that with the little toggle switch over here on the right. So I just clicked temperature. So it's going to stay at 20 degrees. And then I'm going to change the volume of this. I'm going to go from 10 nanometers. I'm going to cut it in half, down to 5. Notice what happened to the pressure. We were at about 1,000 kilopascals. Now we're at about 2,000 kilopascals. So I cut my volume in half and my pressure doubled. So I can go back out to 10. And I get back down to just under 1,000 kilopascals. One of the other laws that we didn't have time to look at today was Charles' law, and it related the the volume and the temperature. And so I just changed it so that the pressure is going to be constant. Notice that the little handle over there on the left is gone. I can't change that, but I can change the temperature. Right now it's at 20 degrees. Now, if I increase the temperature, notice what happens. The volume goes up. If I decrease the temperature, the volume goes down. Okay. Now, I want you to notice each one of these little particles inside this box is a gas molecule or a gas particle. So if you notice, as I heat it up, the molecules start moving faster. It might be kind of hard to see. Let me heat it up a lot. Let's go up to a few hundred degrees Celsius. There's 400 degrees Celsius. Okay, just observe how fast the particles are moving. Now if I cool it down, I'm going to cool it down to, I don't know, let's go down to like minus 150 degrees Celsius. Notice how slow the gas particles are moving. You'll also notice that the pressure went down. Okay, so these are all these variables are linked together. Now, Charles' law specifically relates volume and temperature. So if we hold pressure constant again, we can adjust the volume again with temperature. Now, what's not obvious here is what that relationship is. So let me cool this down until we get down to about 5 nanometers. Oh, we're all the way to the end. Okay, so this is 78 Kelvin. So we have to look at this on an absolute temperature scale, which is the Kelvin temperature scale. So if I take this and I heat it up so that it's twice this temperature, so 78 Kelvin, twice that would be 156 Kelvin. So let's go up to 156 Kelvin. There we go, 156 Kelvin. Notice that the size of the box went from 5 nanometers. Now we're at 10 nanometers. So volume and temperature are both directly proportional. That is, if you increase the temperature, you increase the volume. And if you double the temperature, you double the volume. Now we can't double it again. If we try to go back to room temperature around 300 Kelvin, I think that's, yeah, we can't go big enough for that. But you get the idea. If the temperature doubles, the volume doubles. And that is if pressure is held constant, which we can hold pressure constant and do that. Okay. All right. Well, I hope this has been informative for you. Like I said, you can go to PHET at colorado.edu. Let me go back to their home. And just show you where to go. So if you're here at the PHET simulations, you want to click on simulations right here. And most of the ones that you would be interested in here are the physics simulations. And if you click that and just scroll down, we don't need any of the electricity, light, quantum. It's just these top 4 that really are for us. But down here you can see there's 2 gas ones. There's a gases intro and a gas properties. We were just looking at the gas properties one. But those 2 would be interesting simulations to take a look at. And then the other one that we looked at today in class was the fluids one. I don't remember where that is, but it might be in one of the other ones. But All right. I hope this has been helpful, and I will see you next week.